Start. Hello friends, welcome back to my channel, a physicist Buddhist in California. Uh, those of you who have been following my channel know that I usually talk about some famous book in quantum field theory. I reviewed that book shortly, briefly rather, and I talked about what that book covers and the contents. This time is going to be a little bit different. And instead of talking about famous authors' books, I'm going to talk about what I'm doing myself. So a little bit of that. I'm a physicist. Theoretical physics is my field, and for the last number of years, since 2013, I've been working on an encyclopedia of quantum field theory. Of course, for a number of years, I was just learning the subject and gathering material. And 2017, I started writing it, and so it's been 8 years almost since I started writing it. And so this is what I would talk about. So the question, of course, first, what is quantum field theory, which I've discussed many times. So quantum field theory is a theory of nature which basically allows us to understand the fundamental laws of nature. For example, electromagnetism or nuclear force, and people have been working on gravity also, but that theory is still a work in progress. So the quantum field theory of electromagnetism was the first successful quantum field theory. Successful in the sense that the theory actually gave finite answers to the physically posed questions. For example, if you want to calculate some quantity, some physical quantity, say the energy of electron or the magnetic field carried by an electron, then that's the theory you use. So quantum field theory includes quantum mechanics and Einstein's special theory of relativity. So electron is very, very small, it's very light, so you need to use quantum mechanics, and of course it's also moving at a very high speed, often close to the speed of light. So relativistic effects, which are predicted by Einstein's special theory of relativity, they have to be taken into account. So combine these two and we have a quantum field theory. Of course, there is more to it, but roughly speaking, that's what. So it was first applied to understand some strange behavior of hydrogen atom. Hydrogen atom is the simplest atom. It has one proton and one electron. So in the 1940s, 1947 to be exact, a measurement was made at Columbia University in America, where they found that electron had slightly higher energy than what the previous theory predicted. And this energy was basically could not be explained by the previous quantum theories, quantum mechanics of Schrödinger or Dirac's relativistic quantum mechanics. So what happened is that there are levels, energy levels in hydrogen atoms, which are considered to be degenerate. Degenerate means they are supposed to have the same energy. So these energy levels they are represented as 2s and p. So s, p, d, f. These are how the orbitals are specified in an atom. So the 2s and 2p energy levels or orbitals were assumed to be degenerate in the sense they were supposed to have the same energy, but in fact they were found to be non-degenerate, which means they had a finite energy gap between them. This gap is not very large, it's about 1000 megahertz, but it was a big news, so it was basically electrified the physics community, and people started looking into it. And as a result of that, they produced what's known as renormalized quantum electrodynamics. Renormalized in the sense that they mathematically managed to structure the theory in such a way as to remove the infinities that plague all quantum field theories. So unless you apply renormalization, then a quantum field theory would formally give you infinity as an answer, which is ridiculous because in our universe nothing is infinite. Even universe itself is not infinite. The energy in the universe is not infinite. So how could the energy of a single electron be infinite? But that's what theory predicts. So they managed to remove these infinities that plagued the theory and came up with a finite answer. And so from that, this was 1948-49, and from that point onwards, one could say the dawn of modern quantum field theory began, or renormalizable quantum field theory. So about a decade after that, by early 70s, that same idea was extended to other quantum field theories of nuclear forces. So there are two nuclear forces, weak nuclear force and strong nuclear force. And so their theories were also created by people, very smart people, and they turned out to be also renormalizable. So one could calculate using this theory some values which could then be compared to the experimental values very exactly. The the match between experiment and theory, it's the greatest for electrodynamics, excuse me, for quantum electrodynamics, where they match up to 12 significant digits. The match is not so great for the nuclear theories, but it's still pretty good. So I work in quantum field theory, and 10, 12 years ago, I decided to write an encyclopedia where I would like to gather most of the known information, knowledge about quantum field theory and put it in one place. So this was the idea. So basically that's what I've been working on, and so now I'm up to 4 volumes. So here is one volume that I would like to show you. It's volume 2, part 2. So this is just one volume, and of course, when I say volumes, none of them have been published. So I am in the process of writing, so I don't know when I'll be finished. Maybe by the end of this decade, so it'll be a long time before I'm finished, but I'm working on it, and so it keeps me busy, keeps me occupied intellectually. So it's intellectually very demanding work, but also very rewarding also. So yeah, I would say that probably intellectually it's perhaps the most demanding work anybody could hope to do. But anyway, so that's what I'm doing, and so let me talk a little bit about what I have done so far. So my first volume is mostly uh, non-mathematical in the sense it's qualitative. So I am basically qualitative in the sense I am trying to explain all the phenomena where quantum field theory applies without using mathematics. So that's volume 1. So that's I've made significant progress there. There's still much work to be done there. And the other volume, the volume 2, which has 4 parts. So I just showed you volume 2, part 2. There, of course, I take one topic at a time and I explain that with the full mathematical machinery that's required to explain such a topic. So that's what I'm working on. Now, within quantum field theory, my area of specialization is, because quantum field theory is huge, like I said, it applies to the laws of nature, and people have applied to so many other situations. So I am interested in a type of quantum field theory which is known as conformal invariant quantum field theory. So let me explain. So like I said, quantum field theory requires quantum mechanics extended to infinite number of degrees of freedom, which means that you're not like, unlike the basic quantum mechanics where you just take one particle or two particles or a few particles. Here you make the assumption that you don't have a single particle, you have a wave which is quantum field, and it permeates through entire space of the universe, every space and time, and each elementary particle, for example electron or a photon. So let's say for electron, which is one of the most common particles, our bodies are made of electrons held together by the electromagnetic force which is carried by the photon. So electron is a quantized excitation of a quantum field of electron, And a photon is the same way, is a quantized excitation of a quantum field of electromagnetic force. So these two particles, they come out of these fields. So the fields become more important than the particles. So we are not limiting ourselves to any number of particles. It's the number of particles could be infinite for all we care. What we care about is the fields themselves, so which have infinite degrees of freedom. So these fields can generate as many particles as one is interested in. Anyway, so the quantum field theory, by definition, includes Einstein's special theory of relativity, which requires the cornerstone of special theory of relativity is the invariance of a system, inertial reference frame, for example, when it's moving close to the speed of light. In more technical language, is known as relativistic invariance or Lorentz invariance. Lorentz was the Dutch physicist Hendrik Lorentz, after which this phenomenon is known. So electron in a quantum field theory is Lorentz invariant. Now, what it turned out about 50 years ago, people figured out, this was first done by a Russian physicist named Polyakov. So what they figured out that if you take a quantum field theory, which is Lorentz invariant, and you add another degree of freedom to it, which is known as scale invariance. So scale invariance basically is like, it's easy to understand. Let's say you have you have these parallel lines. Now, if I blow these up, in the sense that I've magnified them by 100 times, they would still be parallel. Okay, or say these two lines are making an angle with, this is an acute angle. Now if I blow it up by 1,000 times again, the lines would still make the same angle. So this is the basic idea behind scale invariance. So it turns out that when you add the scale invariance as another degree of freedom to a Lorentz invariant quantum field theory, it becomes it's much more interesting. Of course, it's interesting to begin with, but it becomes even more interesting. And in certain cases, this theory can be called conformal invariant field theory. There is more to it, but this is, roughly speaking, is what happens when you take a quantum field theory in 3 space dimensions and 1 time dimension. That's the world we live in. So our world has 3 spatial dimensions and 1 time dimension. So if you take a quantum field theory in 3 space dimension and 1 time dimension, and the theory is Lorentz invariant, then if you add scale invariance to it, then it becomes a conformal invariant field theory. Actually, there is one thing I would like to point out. Quantum field theory need not be Lorentz invariant. In fact, there are theories which are not Lorentz invariant, and these are called Galilean invariant theories. Means the speeds at which we move, like at which a car moves or at which a person can run, these are much, much slower than the speed of light. Means Lorentz invariance indicates by name that whatever object you're studying, a subatomic particle most of the time, is moving close to the speed of light. But very few objects in our world move at that speed or anything close to it. So they move at a very small, very low speed. So at objects that are moving at a very low speed, in physics, what the technical phrase we have for them is Galilean invariance. So quantum field theory can also be created for a Galilean invariant system. And there also one can have scale invariance, and you can have, by that same logic, a conformal invariant quantum field theory for a Galilean invariant subsystem. Okay, so these theories are interested. There are people who study a field of physics known as quantum solid state physics. They basically are interested in these theories because in solid state physics you have all these various phenomena like a metal or a conductor or a semiconductor, superconductor, a magnet. So in these such theories, Galilean invariant quantum field theory with scale invariance built into it, they they are very interesting there. On the other hand, the particle physicists, they study these systems which are moving close to the speed of light. So there, the Galilean invariance has to be replaced by Lorentz invariance, and so there you have a conformal field theory, which is Lorentz invariant. So the standard definition of a conformal field theory then comes to mind is the one that's used by particle physicists, that you basically fundamentally assume that the underlying theory is Lorentz invariant, but that doesn't have to be true. The theory could also be Galilean invariant, and you could still have scale invariance in it. Okay, so this is what I've been working on, and so I'm interested in the quantum field theories that apply to elementary particles or subatomic particles. And so I'm interested in studying their conformal invariance and see what happens when you impose this additional degree of freedom to these subatomic particles, how their properties change, and what like really fascinating insights into nature these offer. So I think I would stop here, and I'll be happy to hear your comments if you have any questions. And in my next lecture, I'll continue on this topic. Until then, you guys have a good day. All right. See you soon. Bye.